This is Derf Sites. This functions tutorial is about symmetry. The first kind of symmetry we're going to investigate is y-axis symmetry. Here we have an example function 2x to the sixth minus 3x to the fourth plus 2x squared, and its graph is shown here, and you can see that it is symmetrical across the y-axis. The y-axis is a line of symmetry for this function. On either side it is a mirror image of the other side, like a book that if you were to fold it, these two sides of the book would perfectly match each other if you could do that. Y-axis symmetry has the property for a function that if you look at f at a minus x, it's the same as f at x. Let's take an example here. If we have an x over here somewhere, f of x, we go up and it intersects the graph here at this height on the y-axis. If we look at f at minus x on the other side, it's the same height up because it's a mirror image. That's another way of saying it, is that f at minus x over on the other side of the origin has the same y value, the same graph value. That's what makes it y-axis symmetry. Another way to say it is that if you have the point xy on the graph, such as right here, then negative xy, which is on the other side of the origin at the same height, will also be on the graph. These types of functions are also called even functions because every polynomial with only even exponents has y-axis symmetry. Our example here is a polynomial with only even exponents. Let's look at this algebraically. Here we evaluate our function in our example here at minus x, substituting minus x for x first, and then using the product rule of exponents, because negative x is the same as negative 1 times x, so this becomes negative 1 to the sixth, x to the sixth. Similarly, negative x to the fourth becomes negative 1 to the fourth, x to the fourth. Negative x squared becomes negative 1 squared, x squared. The negatives to an even power, the negative 1s to an even power, become positive 1, and that reduces down to our original function f of x. So f of minus x is equal to f of x because of the even exponents. Our next example is origin symmetry. Origin symmetry is such that if you take a point over here somewhere, its mirror goes over but then flips down, so that we in effect have a symmetry across the origin, somewhat like the propeller of an airplane. Let's look at the details here. It says that f at a negative x is negative f of x. So we have x and f of x here. If we go over to the other side of the origin to where the negative x is, then it'll be the negative, which will flip it down here. And in terms of ordered pairs, if you have an ordered pair x, y, then negative x, negative y is down here. Our example that we're showing here is 2x to the fifth minus 3x to the third plus 2x. Notice it's a polynomial with all odd exponents. These origins symmetric functions are also called odd functions because of the fact that every polynomial with only odd exponents has origin symmetry. Looking at the algebra for this, take our original function here and substitute and evaluate it at negative x, substituting a negative x for x, again using the product rule of exponents. This time we have negative 1 to the fifth, x to the fifth. Similarly, negative 1 to odd powers. A negative 1 to an odd power is a negative 1. That reverses the sign of these terms. Then we can factor out a negative from all three terms, common negative, and we end up with negative the original function. F at negative x is negative f of x. Our next symmetry to discuss logically follows is x-axis symmetry. However, as you can see from our example here, x-axis symmetry is something that can only occur in a relation that's not a function. On either side of the x-axis, it's a mirror image of itself. All of these symmetries are referring to the built-in symmetry of a particular function or relation. We're not looking at two different functions or two different relations and comparing their relative symmetry to each other. This is built-in symmetry. So x-axis symmetry, this relation has built-in x-axis symmetry. If we take a point xy on the graph, then the same x but negative y is also on the graph. Because of that, it will never pass the vertical line test for functions. There will always be 2 points on the same vertical line, at least 2 points, and that rules out any of these x-axis symmetries from being functions. The final symmetry to consider is combined symmetry. Relations can have a combination of symmetries, but if they have x-axis symmetry in them, they will not be a function. Here we have a circle, x squared plus y squared equals 4, and this circle has y-axis symmetry, x-axis symmetry, and whenever a relation has both y-axis and x-axis symmetry, it will automatically have origin symmetry as well, because the y flips it over here and the x flips it down there, and that's equivalent to origin symmetry. In terms of ordered pairs, if we have an xy over here, we'll have an x negative y down here, a negative x and a y up here, and a negative x and a negative y down there. So the 4 equivalent or symmetrical points for the 3 kinds of symmetry in this circle. So summarizing, we've seen for functions y-axis symmetry, and origin symmetry, and for relations, x-axis symmetry, and combined symmetries. This concludes this symmetry tutorial.